You look up at the sky. Everything seems calm. Stars, planets, the view you're used to. But on astronomers' desks, a very different number is in play. 40,000. This is the number of near-Earth asteroids we currently know, track, and follow in their orbits. In other words, objects whose orbits come close enough to Earth's orbit that if the alignment goes wrong one day, they could cause serious trouble. In just the last 3 years, around 10,000 new asteroids have been added to this list. In this video, we're going to talk about what this 40,000 actually means, how much danger we are really in, where the planet-saving DART mission fits into all of this, and maybe most importantly, are the real danger the rocks themselves or our lack of preparation? First, let's clean up the dictionary, because not every rock in the sky is automatically a world-ending doomsday object. Asteroid, rocky bodies orbiting the Sun, mostly found in the main belt between Mars and Jupiter. NEO, near Earth, object, an asteroid or comet whose orbit brings it within a certain distance of Earth's orbit. NEA, near-Earth asteroid, the asteroids among those NEOs. The 40,000 threats we're talking about today are basically these NEAs. PHA, potentially hazardous asteroid, objects that not only pass relatively close to Earth, but are also large enough that, if they hit, they could cause regional or even continental scale damage. According to NASA's current statistics, there are over 39,000 catalogued NEAs. There are about 870 asteroids larger than 1 kilometer, and it's estimated that around 50 more of that size are still undiscovered. For objects 140 meters and above, more than 11,000 NEAs are known, but there may be roughly 14,000 more yet to be found. In short, we know of about 40,000. There could be tens of thousands more we still haven't discovered. How did we reach the number 40,000? In the 1990s, this list was very short. We were talking about mere thousands. Then the telescopes changed. The classic image of an astronomer looking at the sky was replaced by automated survey systems. Catalina Sky Survey, Arizona. Pan-STARRS, Hawaii. Atlas telescopes. ESA's NEO Coordination Center networks. The same regions of the sky are scanned over and over again throughout the night. In each frame, the light points are compared. While the stars remain fixed, if a tiny pixel shifts position, the computer says, "There's something moving here, let's calculate its orbit." Thanks to these automatic systems, around 10,000 new NEAs have been discovered just in the last 3 years. That's why the year 2025 is a kind of milestone for planetary defense. The 40,000th near-Earth asteroid has officially been catalogued. This number is as reassuring as it is frightening, because we know the orbits of these 40,000. The real danger usually lies in what we don't know. Not every rock that passes close to Earth carries apocalypse potential. 3 things determine the danger: size, speed, impact angle, and impact location. Historically, the Tunguska event over Siberia in 1908 is associated with an object around 50 to 100 meters in size. It flattened a forest, but there was no city there. The Chelyabinsk meteor in 2013 was around 20 meters across. It broke up in the atmosphere, but shattered countless windows in the city and injured thousands of people. The Chicxulub impact 66 million years ago is linked to a body several kilometers wide. It's the event believed to have ended the age of the dinosaurs, a truly planet-scale catastrophe. That's why in planetary defense, a critical threshold of 140 meters is used. At that size, you're big enough to cause regional or continental damage. But there aren't that many of you. And the good news: we already know some of them, and we're racing to find the rest. So the phrase 40,000 threats sounds like pure doomsday. But when you dig into the details, the picture looks like this. The vast majority of these 40,000 are either very small or their impact risk for the coming century is very low. The danger is not zero, but it's not random. We are watching, measuring, calculating. Every year, dozens of asteroids pass closer than the Moon to Earth. There's an actual list for this. Asteroids that passed closer than the Moon this year. Most of them are a few meters to a few tens of meters in diameter, small enough that, if they entered the atmosphere, they would likely break up, but still worth tracking. Most of these flybys come and go without any event at all. No news, no headlines, no social media trend. But for scientists, every close pass is a new test, a new calibration, a new, how well are we really tracking this? Exam. Because the core of the issue is this: the 40,000 we see today, are they actually just the tip of the iceberg? In ESA and NASA's own reports, the message is very clear. Yes, 40,000 is a big success, but there are still thousands of large objects out there uncharted, and the real risk lies in them. At this point, a character straight out of a documentary steps on stage: the asteroid hunters. In the deserts of Arizona, on mountaintops in Hawaii, in Chile, in the Canary Islands, they spend their nights at telescope arrays, resurveying the same small patch of sky over and over and over. A researcher from the Catalina Sky Survey, interviewed by Smithsonian, summed up the job like this: what we're trying to do is detect a low probability but high consequence event before it detects us. In practice, they're doing this, taking successive images of the same sky area, letting the computer find the light points that move between frames, measuring the motion and predicting an orbit, having other telescopes confirm anything that looks potentially hazardous. It sounds romantic, but the math is brutal. Among tens of thousands of unimportant rocks, they have to find the truly risky one in time. The earlier you see it, the easier it is to change its orbit. One day, someone effectively asked this: all right, let's say we detect a dangerous asteroid. What do we do after that? The DART mission was the answer to that question. NASA's double asteroid redirection test chose a target that posed no threat to Earth, but could serve as a kind of natural laboratory. Main body, Didymos; small moon, orbiting it, Dimorphos. In 2022, the DART spacecraft performed a deliberate suicide dive straight into Dimorphos. The goal wasn't to destroy it, it was to change its orbit just a little. The result? Dimorphos' orbital period around Didymos shortened by about 33 minutes. This was far above the minimum effect expected. In other words, we have now proven that we can change an asteroid's orbit by hitting it. In the history of planetary defense, this is a turning point. For the first time, Earth is not only the side that watches asteroids go by, but also a player that can, if necessary, reach out and push. DART threw the punch and left, but we still need to study the bruise. That's why the European Space Agency launched the follow-up mission, Hera. Launched in 2024, Hera is on its way to the Didymos Dimorphos system. Its job: examine the crater created by DART, the asteroid's new shape, the change in its orbit, and the debris field scattered into space. New analyses show that after DART's impact, large boulders ejected from Dimorphos behave more chaotically than expected, spreading in different directions, forming clusters, and some potentially interacting with other bodies thousands of years from now. So, yes, we can push the rock, but we're still learning what kinds of side effects that push creates. That's exactly why Hera matters. It's going there to understand the side effects of the weapon we plan to use for planetary defense. Everything we've talked about so far could easily feed into a doomsday scenario. But let's put the picture on the table honestly. According to ESA and NASA's latest statements, none of the 40,000 catalogued NEAs is currently on a confirmed impact course for the coming centuries. That means the odds that we wake up tomorrow to a headline saying, "We forgot a giant asteroid and it's here," are statistically very low, but not zero. And the main risk lies here, in the objects we haven't discovered yet, haven't seen, and haven't added to the catalogue, especially among the approximately 140-meter class bodies capable of regional destruction. A significant fraction is still out there somewhere. The good news: more powerful telescopes, new wide-field survey projects, AI-assisted automatic tracking systems are shrinking this dark zone every year. The phrase 40,000 threats needs to be read correctly. That number is less a cause for panic and more a measure of how much of the unknown we have brought under control. Imagine one last scene. An astronomer on night duty at an observatory in Arizona. Pixels moving on a computer screen. At some point, a tiny light that moves differently from the others appears. Within a few hours, that light's orbit is calculated. Within days, telescopes around the world confirm the object. Maybe that asteroid will miss Earth in the next century. Maybe, 300 years from now, it will make a very close pass. Maybe it will never be a threat. Or maybe it will become the target of humanity's first real defense operation. Right now, we know the two ends of the picture. On one side, 40,000 catalogued objects, orbits calculated down to the minute, an asteroid whose trajectory we successfully altered with DART, and follow-up missions like Hera on the way. On the other side, thousands of bodies still in the dark, pixels not yet visible on any screen, and new first steps waiting to be taken in the future. At the beginning of this video, we asked, what's more dangerous, the rocks or our unpreparedness? Here's the truth. Asteroids are natural parts of the universe. The danger grows when we spot them too late. Our advantage, for the first time, is this. We now have the ability not only to see them, but if necessary, to change their paths. 40,000 threats actually hides one more sentence. We need to be 40,000 times more careful, but we also know 40,000 times more than we used to. And maybe the person who saves Earth won't be a superhero, but a scientist quietly working at a telescope, noticing that a tiny pixel on the screen is moving just a bit differently. For everyone watching, the real question is this: are we going to see this as a disaster story, or as the period in history when humanity finally learned how to truly protect its own planet? The answer depends on how much we choose to listen to science.